Assalamualaikum warahmatullahi wabarakatuh. Okay, for today, our hydraulic class, okay, BFC 21103. Okay, they have 6 topic for this subject, okay, for hydraulic. For topic 1, so introduction to open channel flow. Topic 2 is uniform flow in open channel. Topic 3 is specific energy and control section. And topic 4 is non-uniform flow in open channel. Topic 5 is hydraulic structures. And the last topic for chapter topic 6 is hydraulic machineries. Okay, so now we look at the topic 1, introduction to open channel flow. Okay, introduction to open channel flow is actually for flow in open channel. Okay, for chapter 1, okay, in topic 1. Okay, so for the learning outcomes for this chapter, actually students should be able to define and explain on types and state of flow. Okay, second, to identify types of open channel and define open channel flow, open channel geometries. Okay, actually for open channel flow is the flows of a liquid in a conduit with a free surface subject to atmospheric pressure. Okay, actually this is the open channel flow. Okay, for this the sketch of open channel geometry. Okay, example, flow of water in rivers, canal partially full, sewers and drains, and flow of water over land. So this is the geometries of the channel, open channel flow, actually for the geometries of rivers or canal, okay, for the open channel. So this is the area. Okay, this is T is the top width, and the B is the bottom width, and the Y is the depth of water, and this is the flow, okay, and the free surface from the level of the water. Okay, so this is the example for the channel. Okay, stormwater management road tunnel is the SMART in KL, Malaysia. So this is the Tahan River Rapids. Okay, so this is the example of the open channel flow. Okay, so this is the Siberian Mandarin River. Okay, so actually comparison between pipe flow and open channel flow. Okay, so we have learned the pipe flow in fluid mechanics. Okay, and the open channel flow now we use for the open channel flow. So this the difference between pipe flow and the open channel flow is the fluid completely fills pipes across section and no surface, no free surface. Here for the open channel flow, so actually the liquid flow with upper surface exposed to atmosphere. So this is exposed to the atmosphere. So this is water surface. So this is the channel bottom. Okay, but this is for the pipe flow. Okay, this is a pipe flow. Okay, they have the hydraulic grade line and energy line. Okay, but for the open channel, they just only have energy line. Okay, fluid flows under pressure for the pipe flow, and open channel flow, the flow due to gravitational force. Okay, slope influence. So they have the slope here. Okay, and the hydraulic grade line does not coincide with water surface. So, but for the open channel flow, the hydraulic grade line coincides with water surface here. So they have the water surface here. Okay, maximum velocity occurs at center of pipe flow. And for the open channel flow, the maximum velocity occurs a little distance below water surface. And the last velocity distribution is symmetrical about pipe axis here. So they have the symmetrical here. And the velocity distribution depends on channel roundness here. Okay, so the open channel, so they have also channel roundness. Okay, so the practical application of this open channel: A, flow depths in rivers, canals, and other conveyance conduits. Okay, change in flow depth due to channel control, especially example as weirs, spillways, and gates. So we will cover this spillway and get as the structure, hydraulic structure. Okay, and the C is change in river stage during floods, surface runoff from rainfall overland, and the optimal channel design and others. So this is the application of open channel. Okay, so the flow parameters and geometrical elements. So we must know that the depth of flow Y is the vertical measure of water depth. Normal depth D is measured normal to the channel bottom. So actually for most application D is equal to Y when the angle here is less than 10%. Okay, example as cos 1 theta degrees 1 degrees is equal to 0.9998. Okay, actually this is the concept for the water surface slope and the water level here, the free surface, and we have the bottom slope here. Okay, now we look at the flow or discharge. Q is the volume of fluid passing across section perpendicular to the direction of flow per unit time. Okay, so this is the discharge Q. Okay, mean velocity V is the discharge divided by the cross-section area. V is equal to Q divided by A, area. Okay, Q is the discharge, V is velocity, then A is the area. Okay, so weighted parameter P is the length. Okay, the length of this here, P. The length of channel parameter that is weighted or covered by flowing water here. Okay, so we have the water here. Okay, and this is the weighted parameter P. Okay, we have the B is bottom width and the T is top width. So A is the cross-sectional area covered by flowing water. Okay, so hydraulic radius. Okay, actually this is the properties of the channel here. Okay, hydraulic radius or R is the ratio of the flow area A to weighted perimeter. Okay, so R is equal to A over P. Okay, area divided by perimeter, weighted perimeter A over P, and the hydraulic depth is the average depth of irregular cross section. Okay, D is equal to flow area divided by top width. D is equal to A divided by the T here. So we know that the T is the top width here, B is the bottom width, and the A is the flow area here, and the P is weighted perimeter. Okay, so this is the drawing from JKR standard surface drain. Okay, 2014. Okay, so this is the standard drawing for the drain type. Okay, so the drain type. Okay, this is an example that you will learn after you work inside. Okay, so the public works department JKR standard surface drain. So we know that the types of the drain. Okay, types of drain with the rectangular. Okay, and this one and so on. So this is type of the using the drain type of the triangular. Okay, so this is type of the triangular. Okay, so now we look at the table open channel geometries, the channel sections, area, top width, and weighted perimeter. Okay, we have the triangular, trapezoidal, and circle. Okay, for the rectangular, we have the area is B, is bottom width, times by the Y. Y is the depth of flow, so the BY here. Okay, top width is the B, is equal to the B, because this is rectangular. And the weighted parameter P is B plus 2Y here. So that's why B plus 2 times Y. Okay, they have 2Y here. Y here and Y here. So that's why B plus 2 times Y. Okay, for the triangular, Z times by Y, power of 2 here is the area. And the top width 2 times by Z times by Y. And the P so on here. Okay, so don't worry about these geometries because all this table is given to you in your test or in your final. Okay, so you just know how to find the area, how to find the top width here T, and how to find the P based on your different types of these geometries channel section. Okay, rectangular, triangular, and trapezoidal, and also circle. Okay, now the activity 1.1 here. So we have the rectangular channel. Okay, so in these questions, ask you to find the top surface width, to find the T here. Okay, and find the flow area of this channel. Okay, weighted parameter to this one P, and hydraulic radius, okay, R of this channel. Okay, if Q is given as 2.4 meter cube per second, determine the state of flow. Okay, actually for the state of flow, so we will use at the previous slide. Okay, so we find first the T, weighted area, weighted parameter, and hydraulic radius. Okay, so Z, okay, to find the Z, because we know that because we have the Y here, okay, and we know about the angle here, so we must find the Z here. Okay, you want to find the Z here. Okay, to find the Z here. Okay, what is the distance here to get the Z? So Y over Z here. So that's why you use the Z is equal to Y over tangent 60 degrees, is you get the 0.5774, and you find the T using this equation. T is equal to B plus 2 times by zy here. Okay, and just put all the value here, so you get the T. Okay, and use the equation of the area, so you get the B times by the Y, okay, plus the zy squared. Okay, so you just put the value here, so you get the area. Okay, now you find the perimeter here. Okay, find the perimeter. Okay, just put the B and Y, and you get the P is 7.619 meter. Okay, so and find the R, to find the hydraulic radius R. Okay, R is equal to A divided by P, so you get the R is 1.091 meter. Okay, so this is the concept to find the T, to find the weighted area, to find the weighted perimeter, and hydraulic radius. Okay, so if Q is equal to 2.4 meter cube per second, determine the state of flow. Okay, actually for the state of flow, you must find the velocity. Okay, after you get the Q, so if you know that the Q is given to you, so you use the Q is equal to AV. Okay, so actually this, this from this Q is equal to AV. Okay, this is the so this is the equation for discharge. Okay, area times by the velocity, so you get the discharge. Okay, to find the velocity, so the discharge divide by the area. Okay, so the Q is given to you, so and you get the area. Okay, so you get the velocity is 1. Okay, so use the front number here to determine the state of flow. Okay, and also use the front number and Reynolds number. Okay, to determine the state of flow, you must find using the front number or Reynolds of number. So these two equations, so we will cover in the previous slide. Okay, so now we look, this is activity, so this is also the activities 1.2, how to find the flow area of this channel. Okay, and find the weighted perimeter for this. Okay, weighted meter is actually along this one. This is the that I highlight with the yellow color is the weighted perimeter that you must find. Okay, so this is the weighted perimeter and the hydraulic radius of this channel. So you must divide to this. Okay, So you must divide this channel to 1, okay, 1 channel, 2 channel, 3, 4 and 5. So you just divide to the 4 channel. Okay, so you just put the flow area. Okay, you must step by step you use the area 1 to get the total area. So you must find the area 1, area 2, area 3 plus area 4 and plus area 5. Actually, area 5 is this one. Okay, area 5 is this one. You get the area of A5. Okay, so you get the area of 5 here. Okay, so this is area of 5. So you get this one. Okay, area of 1, area 2, area 3, 4 and 5. So step by step you must find. Okay, so area A1. Okay, area 1. So you just get the triangular here. Okay, A2 is rectangular. A3 is also rectangular, and this also rectangular, and this is triangular. Okay, so you get this one. Okay, A1, A2, A3, A4 and A5. So you get the Z1, Y1 squared plus B2, Y2 is rectangular, and also B3, Y3 and B4 times by Y4, and plus the triangular at the A5. Okay, so you get the B is bottom width. Okay, Y is the depth of, okay, the depth of, okay, the depth of water here. Okay, so you get this one. So just put the value here until you get the area is 31.5 meters squared. So you get step by step. Okay, you just calculate between section 1, section 2, section 3, 4 and 5 to get the area. Okay, now you look at the weighted perimeter. So weighted perimeter is actually at the section 1 also here. So you have the, okay, I just highlight using the, okay, the red here. Okay, so you must know the highlight here. Okay, the highlight with the red here is the perimeter. Okay, weighted perimeter that you must to find. Okay, so the A1 here, so you must find the P1 here. Okay, so the P3, okay, at the P3 here is one P3. Okay, this A1, this is the A2, okay, A4 and this one. So that's why you get the perimeter 1 and the weighted perimeter 3, weighted perimeter 4 and 5. Okay, for the weighted perimeter 1 here, so you get this one. Okay, and the A2 here is 2 meter. Okay, and get the 2 meter. So you get the, okay, 2 here. Okay, 2 plus 3 minus 1 is 2 also. So 2 plus 2. Okay, so you get the 2 meter plus the 2 meter also. So this is the length here. Okay, with the perimeter, and you must find the length here of the A3. Okay, and the length here is 3 meter plus the flow depth here 2 plus 1. So the 3 meter plus 3 meter. So you get the 3 meter. So this one 3 meter plus 3 meter, and this is 2 plus 2. Okay, actually 2 plus 2 here actually for the this side. 2 meter plus 3 here minus by 1 here. So we get the 2. Okay, that's why you get this one. Okay, and this one, and this one using the equation of this one. Okay, so you use this one. Okay, this equation here y5. Okay, in using this table here. And this one. Okay, using this table. Okay, to triangular. Okay, so you get, after you get the perimeter, where the perimeter is 17.07 meter here. Okay, after you get the area and you get the P here, so you just using the R is equal to A over P. So you get the R is 1.856 meter. Okay, so this is the step by step how to find the area, how to find the weighted parameter, and how to find the R. Okay, so now we know that the types of open channel. Okay, types of open channel, they have the prismatic and non-prismatic channel. Okay, prismatic channel is the channel which cross-section shape, size, and bottom slope are constant. Most of the man-made artificial channels are prismatic channel over long stretch. Example of man-made channels are irrigation canal, flume, drainage ditch, roadside gutter, drop, chute, culvert, and tunnel. So this is example of the prismatic channel. Okay, so all natural channels generally have varying cross sections and therefore are non-prismatic. Okay, actually for all natural channel is non-prismatic. Okay, example of natural channels are tiny hillside rivulets through brooks, stream, rivers, and tidal estuaries. Okay, estuaries. Okay, so this is the non-prismatic and the non-prismatic. Okay, rigid and mobile boundary channel. Okay, rigid channels are channel with boundaries that is not deformable. Okay, so this is the definition of rigid channel. Okay, channel geometry and roughness are constant over time. Typical example are line canal, sewers, and non-erodible unlined canals. So this is the rigid channel. Okay, mobile boundary channels are channels with boundaries that undergo deformation due to the continuous process of erosion and deposition due to the flow. Okay, examples are unlined man-made channels and natural rivers. So this is mobile boundary channels. Okay, so this is the definition of the types of open channel. Okay, so canal is usually a long and mild slope channel built in the ground, which may be unlined or lined with stone masonry, concrete, cement, wood, or bituminous material. Okay, the example is Terusan Wan Muhammad Saman in Kedah. Okay, and also the Terusan the Griboyedov Canal in Russia. Okay, so the flumes is the channel of wood, metal, concrete, or masonry usually support on or above the surface of the ground to carry water across a dispersion. Okay, so this is the flume diverts water from White River, Washington to generate electricity. So this is an example of the flumes. Okay, and the Bull Run hydroelectric project division flume here. Okay, so this is the open channel flume in laboratory. So this is also have in our laboratory in FCAP. Okay, so you can look at this. So actually this is the main laboratory that you will use to get the flow depth, you get the area of the water surface here, okay, through this flume. Okay, so the chute is a channel having steep slope here. So the natural chute or falls on the left and man-made logging chute on the right on the Quebec, Canada. So this is the example of chute. So the drop is similar to a chute, but the change in elevation is within a short distance. So this is the spillway. Okay, the spillway is actually they have the drop here. Okay, the drop from this spillway diversion dam is vertical hard basin drop structure designed to dissipate energy. Okay, stormwater sewer is a drain or drain system designed to drain excess rain from paved street, parking lot, sidewalks, and roof here. So this is this is called the stormwater sewer here. So the runoff here. Okay, storm drain receive urban runoff. Okay, and also the storm sewer here. Okay, so the type and classification of open channel flow we can divide to the two here: steady flow and unsteady flow. Okay, and steady flow and unsteady flow is can conclude to the uniform flow and non-uniform flow. Okay, so non-uniform flow we will cover the rapidly varied flow and gradually varied flow, in which we cover in topic 3 and topic 4 and 5. Okay, rapidly vary flow and gradually vary flow. Okay, in topic 3, 4, 5. Okay, for non-uniform flow. So uniform flow is in topic 1 and topic 2. Okay, actually that we have covered here. In topic 1 is uniform flow. Okay, so open channel flow conditions can be characterized with respect to space or uniform or non-uniform flow, and times using the steady or unsteady flow. Okay, so now space, how do flow conditions change along the range of an open channel system? Uniform flow, depth of flow is the same at every section of the flow. Dy over dx is 0. Okay, non-uniform flow is depth of flow varies along the flow. Dy over dx is not equal to 0. So we call here as the non-uniform flow and uniform flow. Okay, so uniform flow, so you can sketch the uniform flow here. The depth of flow is the same, okay, at the every section along the channel. So the dy over dx here is equal to 0 because it's the same at every channel. Okay, but non-uniform flow, the depth changes along the channel, okay, from the y to y2, so the depth is not same. Okay, so but the uniform flow, the depth from the y here to the y2 here, so it's the same. So the depth of flow is the same at every section. Okay, the depth of flow varies at different sections along the channel. So dy over dx is not equal to 0 for non-uniform flow. So you can explain this concept for uniform flow and non-uniform flow if in your test or in your final ask you to explain briefly about these two types of flow. Okay, so you can explain and sketch the uniform flow and non-uniform flow here. Okay, sketch here and sketch here for the uniform flow. Okay, with the time, how do the flow conditions change over time at a specific section in an open channel system? Okay, steady flow. Steady flow is depth of flow does not change or constant during the time interval under consideration. So dy over dt is equal to 0. Okay, but unsteady flow is depth of flow change with time. Dy over dt is not equal to 0. Okay, so steady flow. So time 1 to time 2 is equal. Okay, so because the y1 is equal to y2. Okay, depth of flow is the same at every time interval. So dy over dt is 0. For an unsteady flow, so it's not the same. Okay, y1 is not the same as the y2 is not the same as the y3. So that's why depth of flow change from time to time. So dy over dt is not equal to 0. Okay, so the flow is rapidly varied if the depth change abruptly over a comparatively short distance. So example of rapidly varied flow, hydraulic jump, okay, hydraulic drop, flow over weir and flow under a sluice gate. So we will cover this rapidly varied flow in topic 3, 4 and 5. Okay, topic 3, okay, for rapidly varied flow in hydraulic jump. Okay, so the flow is gradually, so gradually varied flow is the depth change slowly over a comparatively long distance. Okay, example of gradually varied flow are flow over a mild slope and the backing up of low backwater. So the gradually varied flow. So we cover it in topic 4. Okay. Topic 3 for rapidly varied flow. Topic 4 is gradually varied flow. Okay. So now we can look at the sketch here. Okay. For the hydraulic jump. Okay. Hydraulic jump is rapidly varied flow. Okay. So we can know that this is concept of rapidly varied flow. Okay, and at the after the contraction below the sluice here, so we give the gradually varied flow, and the hydraulic jump is rapidly varied flow, and this is the gradually varied flow until you get the RV is rapidly flow over weirs and gradually varied flow here, and at the hydraulic drop is also RVF. Okay, actually the comparison between gradually varied flow and rapidly varied flow. Okay, you can maybe you can sketch and you explain about the gradually varied flow and rapidly varied flow if in your test or in your final ask you to explain briefly, or list what is the difference between RVF and GVF. Okay, so 1.4 point here is the state of flow. So we used to get the state of flow using the viscosity and gravity effects relative to the initial forces of the flow. So it's depending on the effect of viscosity relative to initial force to the laminar, turbulent or transitional state. Okay, so effect of viscosity. Okay, using the Reynolds number that I mentioned there in activity 1.1. Okay, to find the state of flow, so we can use the Reynolds number and also the Froude number. So now at the state of flow, so we use the Reynolds number. It represent the effects of viscosity relative to inertia. Okay, so R is Reynolds number is equal to velocity times by the R hydraulic radius divided by the viscosity. So this using the Reynolds number. Okay, where V is the velocity, R is the hydraulic radius of a conduit, and the V is kinematic viscosity for water at 20 degrees Celsius. So we get the velocity here, viscosity. Dynamic viscosity is this one. So actually for this type of viscosity and dynamic viscosity, density is given, okay, in your question for in your final or in your test. Okay, so using the Reynolds number, if the Reynolds number is less than 500, so the flow is laminar. Okay, the Reynolds number is between 500 to 2000. 500, the flow is transitional, and more than 12,000, this is a flow is turbulent, more than 12,000 here, so the flow is turbulent. Okay, so using the Reynolds number here. Okay, the flow is laminar if the viscous force are dominant relative to inertia. Okay, viscosity will determine the flow behavior in laminar flow. Water particle move in definite smooth paths. Okay, so the flow is turbulent if turbulent here if the initial force are dominant, then the viscous force in turbulent flow, water particles move in irregular paths which are not smooth. Okay, so when using the effect of gravity, to know that the state of flow is subcritical, critical and supercritical, so we use the Froude number. Okay, the Froude number represent the ratio of initial forces to gravity forces is using here. Froude number is equal to V is divided by the gravity here times by the D here. Okay, so use this equation, okay, for Froude number and Reynolds number. So the Froude number, so less than 1, so we get the subcritical state. Is equal to 1 is a critical state. More than 1, the flow is supercritical state. So this is using Froude number to know that the state of flow. Okay. So regimes of flow, a combined effects of viscosity and gravity using the Froude number and Reynolds number may produce any one of the following 4 regimes of flow in open channel. Okay, we have subcritical laminar when Froude number less 1 and Reynolds number is less 500. Okay, supercritical laminar when Froude number is more than 1 and the Reynolds number is less than 500. Okay, supercritical turbulent when Froude number is more than 1 and Reynolds number is more than 12,500. Okay, and so on. So subcritical turbulence when Froude number is less 1. This is Reynolds number is more than 12,500 here. Okay, so this is the regime of flow. That's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh. If you have any questions, you can ask in our group. Okay, that's all. Thank you.